Good morning everyone, my name is Saw Jia Yi and I am here today to present my project under INOTEK. The project is titled Metric-Driven Design and Verification of Low Power Mixed Signal SoC. This project is about the design process of an 8-bit asynchronous side ADC using 45nm CMOS technology. Side ADC are attractive circuits for applications that require low power with medium resolution and medium speed, such as computing in-memory CIM architecture for AI application and low power sensor interface for biomedical system. The asynchronous architecture allows the ADC to operate without the need for an oversampled clock, reducing the design complexity associated with higher frequency. The first objective of the project is to design a 1V 8-bit asynchronous side ADC in 45nm CMOS technology that meets performance metrics such as an INOTEK of at least 7-bit, an SNR of 46 dB, and a low power consumption of approximately 50 microwatt. The second objective is to verify the design low power mixed signal SoC through metric-driven simulation, ensuring that the system achieves a figure of merit FOM of around 50 fertajoules per conversion state, making it suitable for energy-sensitive applications like wearable and IoT devices. Now I'm going to proceed with the methodology part. First is internal clock generator. The internal clock generator is the block responsible for providing the rest of the system with a clock signal to operate. This block produces two output signals, clock sample and clock SAR, and receives three inputs, clock external, ready, and EOC. This is the schematic diagram of internal clock. The second circuit design I want to discuss is process sample and hold. The sample and hold circuit is basically a switch that captures the value of an analog signal at a certain moment and holds it constant for a certain amount of time. The bootstrap switch helps mitigate some of the switch non-idealities by keeping the switch VGS fixed during the sampling phase. So Vin is the analog signal and Vin sample is the signal after the sample and hold circuit. This is a test band for bootstrap sample and hold. The third circuit design is capacitive DAC. The capacitive DAC uses charge redistribution to convert the digital code coming from the SAR logic into the corresponding analog voltage level to be compared by the comparator. This is the low level and top level schematic of capacitive DAC. This is the test band for capacitive DAC. This is the corresponding transient response of the test bench. For the waveform, we knew that the 8 resolution bit D7 to D0 are correctly loaded, showing the correct functionality of capacitive DAC. The fourth circuit design is dynamic comparator. The comparator function is to compare the analog input level coming from the DAC and to produce a digital output bit, either high or low, representing the result of the comparison. A high-speed, low-power strong-arm comparator is used. This is the low-level and top-level schematic of dynamic comparator. This is the test band for dynamic comparator. This is the corresponding transient response of dynamic comparator test bench. Okay, from the waveform we knew that when Vin P is larger than Vin N, the output bit will be 1, and then when Vin N is larger than Vin P, the output bit will be 0. Okay, the bits in input and output are the same, showing the correct functionality of dynamic comparator. The final circuit design is SAR logic. The SAR logic generates the digital code for the DAC in each comparison stage. At the end of the conversion cycle, the final digital code is produced by an output register. The flip-flops used are TSPC flip-flops with asynchronous set and reset inputs. This is the schematic diagram of SAR logic. This is the schematic diagram of output register, and this is the schematic diagram of output DAC. Now I am going to proceed with the result and analysis part of the project. This is the test band for SAR ADC, and this is the corresponding transient response of it. From the waveform, we knew that the final signal shows the stepwise line pattern indicating that the correct functionality of the SAR ADC system. This is the spectrum waveform and output measurement for SAR ADC test bench. From the output measurement, we knew that the enum is 7.02 bits and SNL is 44 dB. The verification of enum and SNL has been done. The total power consumption of SAR ADC is 1.097 mV and capacity DAC accounted 70% of it. To analyze this, all power bits of internal clock, capacity DAC, comparator and SAR logic are measured and recorded. For the table, we knew that the relay P-pin of capacity DAC consumes the most power, which is 725.6 MW. To analyze why relay P-pin in capacity DAC consumes so much power, all capacitive DAC relay P-pins are selected for voltage and current variation. From the corresponding transfer response, we knew that the high current spike on every capacitive DAC relay P-pin causes high power consumption for capacitive DAC itself and overall system. This is because in power equation P equal to V times I, when voltage supply is fixed, current becomes major effect that can affect the power. The least current has 3 mA and the highest can go up to 4 mA. The large current spike for relay P-pin during capacitive DAC switching will cause reference voltage drop and supply noise. These disturbance will couple into sensitive blocks such as the comparator and sampling network. The increased noise at the comparator input leads to higher decision uncertainty, and the non-ideal setting will trigger additional switching activity in the SAR logic and internal clock. Therefore, reducing capacitive DAC reference power will not only lower direct tech energy consumption, but also stabilize reference and supply node and reduce unnecessary switching and dynamic power in surrounding blocks. Capacitive DAC and reference path optimization is therefore critical for improving overall power efficiency and figure of merit. This is a performance summary of SAR ADC system and its corresponding overall verification. This is a benchmark table of the project. Now I'm going to proceed with the novelty and inventiveness part of the project. This will demonstrate a complete low power SAR ADC designed and verified at the transistor level, providing a realistic implementation beyond behavioral modeling. The project offers practical insight into real-world limitations of mixed-signal circuit, including non-ideal switching behavior and power-related constraints. By analyzing the circuit operation in details, key factors affecting power efficiency and commercial performance are identified and clearly linked to measured metrics such as power consumption, enum, and sampling rate. Overall, this work established a strong connection between transistor-level circuit behavior and system-level ADC performance while providing a solid baseline design for future optimization. Now I'm going to proceed with the potential of commercialization part of the project. This will demonstrate strong commercialization potential by delivering an energy-efficient SAR ADC with balanced resolution and speed, well aligned with the needs of modern portable and embedded systems. The design is well suited for integration into mixed-signal SoC platform, enabling compact, low-cost solutions for large-scale deployment. Furthermore, compatibility with advanced CMOS technology also ensures scalability, manufacturing efficiency, and a clear pathway toward cost-effective commercialization. Now I'm going to proceed with the SDG part of the project. This project aligns with SDG 9, Industrial Innovation and Infrastructure, by contributing to innovation in low-power mixed-signal integrated circuit that support future electronic infrastructure. By emphasizing energy-efficient data conversion and transistor-level optimization, the work addresses the growing demand for reliable and sustainable electronic systems. Low-power SAR ADC play a critical role in enabling scalable embedded platforms, sensor-based systems, and intelligent electronic applications where efficiency and integration are essential. Overall, this project supports the development of advanced semiconductor solutions that promote sustainable industrial innovation and long-term technological growth. Thank you.